Hey guys! So classmate asked, what is kinetics and can you do some practice problems relating to rate laws, reaction mechanisms, and methods of initial rates? So put simply, kinetics is a study of the rates of reactions. In chemistry, a reaction's rate can be calculated in terms of how fast the concentration of a substance changes in the course of a chemical reaction, basically molarity over time. Remember that molarity is how we calculate the concentration of our substance. And note that brackets are how we represent a concentration. Therefore, if we want the rate of reaction in terms of its products, we would say that the change in concentration of a product over time equals the rate of the reaction. Similarly, the change in concentration of a reactant over time equals the rate of the reaction. But this time, we put a negative sign in front of the ratio, because reactants go away in a reaction, and since we do not want a negative rate, we put a negative outside of the ratio to create a positive number. This means that all rates of reaction will be positive. Now let's see an example with relative rates. Let's say we have the reaction 2N2O5 produces 4NO2 plus O2. This can be represented as negative change in concentration of N2O5 over time, because rate of reactions with reactants will have a negative sign in front of it, equals 1/2 change in concentration of NO2 over time. This positive 1/2 coefficient comes from the fact that a product's rate of reaction will not have a negative sign in front of it, and that going from NO2 to N2O5 is a change in 1/2, since 4 times 1/2 equals 2. This rate is also equal to 2 change in concentration of O2 over time. The positive 2 this time comes from the assumed 1 coefficient before oxygen in our equation, and that multiplying by 2 gets us the coefficient in front of N2O5. Now that we are comfortable with rates of reactions, let's learn more about rate laws. A rate law is written in the form rate law equals the rate constant K times the concentration of each reactant to a certain order. In the following example, we will be finding out the values of our rate laws through reaction mechanisms. Reaction mechanisms are stepwise reactions that describe an entire elementary reaction. In this example, the first equation is an elementary reaction, and so far all problems we have been doing and are used to solving deal with these elementary reactions. These smaller reactions in red are called mechanisms, and once combined, they create our elementary reaction. To do so, cancel out the compounds that exist in both the reactant side and product side of our mechanisms, in this case HOI and 2 hydroxides. Our remaining compounds combine to get our elementary reaction. Now what we canceled out is actually important in determining whether the canceled out compound was an intermediate or a catalyst. Note that intermediates will always be present in our mechanisms, but catalysts will only be there sometimes. Intermediates show up first as a product, while catalysts will show up first as a reactant. Since HOI and hydroxide appear in our mechanism first as reactants, they are intermediates, and there are no catalysts in our reaction. From here, we can draw an energy profile of our reaction. An energy profile is representation of the pathway of the energy change from reactants to products. It's actually very simple to draw. All you need to do is count how many mechanisms there are and take note of which ones are fast and which ones are slow. Luckily for us, the equations already say which is which, with the first mechanism being slow and the other two being fast. Therefore, we draw one big hump representing the slow step and 2 smaller humps representing the other 2 fast steps. This is because the slower step represents more energy taken in the reaction to overcome the bigger hump, while the 2 faster steps require less energy and have smaller humps. The 2 fast humps don't even have to be the same size. Just make sure that the tallest hump is the slowest mechanism. Now let's try to find our rate law. For this part, all we have to do is focus on our slow step of the mechanism, or in this case, H2O2 plus I- produces HOI plus hydroxide. Remembering that our elementary reaction is what is written in blue, and that our rate law is what is written in green, we can replace X and Y with the reactants in our elementary reaction, H2O2, I- and H+. Now we must find the orders of each reaction. Referring to the slow step of our mechanism, we see that H2O2 and I- has an assumed 1 coefficient, meaning that it's first order with respect to H2O2 and I-. h plus is not present within our slow step, meaning that it is zero order with respect to h plus, and therefore gets a zero coefficient. Since 0 to the power of anything is just 1, our final rate law is rate law equals k times h2o2 to the power of 1 times I minus to the power of 1. Now so far our rate law has been based off the equations that we have and not any actual data. If we were to be given data about the concentrations of our reactants, initial rates, and so on, we would need to use methods of initial rate to determine our rate law. In this example, we need to find the reaction order of NO2 and F2. Knowing that rate equals K times concentration of NO2 to some order times F2 to some other order, we solve for X and Y. To start off, we need to put in some values. In this case, we will choose F2 concentrations that are similar to each other so that they will cancel out in our equations. Using 0.0318 and 0.0315 for our concentrations of F2, we get these two equations. Remember that all our values come from the table above, and we just plug them in to their corresponding role in the rate law equation. Now we divide these two equations by each other, canceling out similar terms, such as the concentration of F2 and the constant K's. Note that the values don't have to be exactly the same to cancel out, just similar. When we divide the rate laws and concentrations by each other, we get 4.05 equals 4.02 to the power of x. When x equals 1, we get 4.02, which is close enough to 4.05, meaning that it is first order with respect to NO2, since that is the value we did not cancel out. Now let's solve for the order of F2. Now we look at NO2 values that are close to each other, and we see that it is 0.0482 and 0.0480. Looking at the corresponding data, we can get the equations, written here in blue. Note the concentrations of NO2 are to the power of 1, because we already know that they are respect to the first order. Again, we are going to divide and cancel out similar numbers, getting 0.251 equals 0.250 to the power of y. Again, y will now become 1, meaning that it is first order with respect to F2. From here, we can determine the rate law and overall order of our reaction. Our rate law is K times NO2 to the power of 1 times F2 to the power of 1, meaning that our overall order, which is just the sum of each reactant's individual order, is 2. Now to find our rate constant K. To do so, we will just be using the data from experiment 1. With the rate law that we made before, we put in these values for our knowns, getting us 1.90 times 10 to the negative 3 equals K times 0.0482 to the power of 1 times 0.0318 to the power of 1. Solving for K, we get 1.24. But what's our units? A quick shortcut to remember is that rate constant K equals 1 over T times molarity to the power of our overall order minus 1. Since our overall order is 2, and time is calculated in seconds for our data, the rate constant's units are 1 over seconds times molarity, meaning that our rate constant is 1.24 per seconds times molarity. I hope this video helped you to understand kinetics and its different applications in rates of reactions, rate laws, reaction mechanisms, and methods of initial rates.